Okay, let's go over some questions from the study guide that my teacher gave me. Um, this first question asks us, so we're given a force here, and it wants us to resolve into components along x and y. So let's draw a free body diagram. This is the x-axis, this is the y-axis. The force is coming in this way at a 15-degree angle along against the y. So force in the x direction is going to be this one right here, which is opposite, which is going to be sine, and this is 120. So 120 sine, oh wait, what happened? Oops, sine 15. And the force in the y direction is going to be 120 just cosine 15 because it's adjacent, which is this right here. Okay, now using the scalar approach, find the magnitude and direction of the moment about point B. Okay, so using the scalar approach, we need a distance, the moment arm, which is, let's call L, times the force perpendicular, which is this x component right here, which we already have. So let's write moment at B is going to be equal to L, which is the moment arm, times the force perpendicular, which is Fx. So what is L? We can find L by doing a triangle and then applying some trig. So we're told that this is this is 10, this is 150, and this is L, this is 55, yeah, 40 plus 15, which is 55. Let's do some law signs. L over sine 150 is equal to 55 over sine 10. Calculate this. L is going to be equal to 158.4 millimeters. Okay, now that we have this, we can just plug it in. MB, the moment about B. Also, F in the y direction is in the negative direction. It's going down. I forgot about that. Here it asks us for the magnitude and direction. Let's take a look at the direction. It's going this way, which is going to cause a moment, and clockwise, which is going to be negative. So moment B is going to be equal to negative L times Fx. It's going to be 158.4 times 120 sine 15. Now that we have this, we can do, let me just calculate it, right? MB is going to equal to negative 4920, and this is going to be Newton times millimeters. Take a look at part B, resolve into tangential and normal at point O. So the normal is going to be this right here, because this is tangential. This is aligned with the hip, which is force tangential. And the normal is going to be perpendicular, 9 degrees, which is this right here. This is the force normal. We need the force normal because it also asks us to find the moment about point A, which is right here. And we can just do this moment arm, which is 55, times this. So to do that, we need to finish our free body diagram. So if we have y-axis extending all the way out, this extending over here, actually we don't need that. The hip goes something like this, and this is 20 degrees. We know that because this is 20 because 10 plus this, triangle, 180 minus both of those is equal to 20. And based on vertical angles, we know that this entire thing is 20. So 20 minus 15 is 5. So this is 5 degrees. It's right here. And this is going down, blah, 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 blah. And then we have and then our normal will be like this. And our, yeah. So if we write it out, force tangential is going to be in the negative direction because this arrow is going down. So it's going to be in line with this arrow, which is going down, yeah. So it's going to be negative. It's going to be 120. And then we'll just times sine 5. Let me see if that's right. That looks right. Yeah, I think that's right. Tangential, along with that. Okay. And then the force normal is going to be equal to negative 120 cosine 5. Now it wants us to find the moment about A, and the moment about A is going to be equal to the moment arm, which is 55 we said earlier, times the force normal, which is going to be, let's just write it out, force normal, which is going to be equal to 55 times negative 120 cosine 5. And taking a look at the magnitude, I mean the direction, we know that's going to be in the positive direction because it's this way. So we actually don't need this negative sign, so just do positive sign there. So moment around A is going to be equal to 418.4 Newton millimeters. Okay, now part C. Using a vector approach, find the force about A. So obviously, this operation should explicitly use cross product. Okay, obviously. Obviously it says vector approach, so what difference, if any? There's not going to be a difference because moment about A is moment about A. I don't see there wouldn't be any difference. Okay, so we're finding it about A. So this is our point. So let's find, okay, so moment about A, so vector approach. This is going to be equal to a vector from A to O. So we need a vector from this to this, cross this force right here. A vector A to O, cross force. We need our force, the vector force, which is going to be, we already have that here, up here. So force is going to be equal to 120 sine 15I minus 120 cosine 15j. So we have this. And we need a RAO, which is going to be equal to RO minus RA, which is going to be equal to O, which is 0, 0, 0. A is, okay, I kind of did it in 3D. I don't know why I did that. There's probably a better way to write this. So if we just look at the x direction first, right? It's going this way, which is negative x, and it's going, oh my goodness, what is this? Okay, 55 or 40. So we have a triangle like this, and this is 40, and we have this angle right here, which is 20, and okay, is that all we're given? Like, what the heck, bro? I think that'll be fine. And the x direction is negative, so let's write negative. And then we want this adjacent, no, we want this opposite, which is this is the x, this is the y, right? So we want the opposite, so it's going to be 40 sine 20. 40 sine 20 in the I direction. And then in the y direction, we are going up from here to here. So it's going to be positive cosine, right? Plus 40 cosine 20 in the j direction. Now that we have that, we can just do a cross product. It's pretty simple. So it's going to be this. So MA is going to be equal to IJK negative 40 sine 20 40 cosine 20 0, and the force is 120 sine 15, which is this right here basically, negative 120 cosine 15 0. And I'm sure you know how to do a cross product. It's pretty easy, so we're just going to delete this. If you do I, it's going to be 0. If you do j, it's going to be 0. If you do k, so we're only going to get a k value basically. So just do it yourself. I don't really want to do it. It's 418.4 Newton millimeters K direction. So that's the moment and no diff. So let's check if there's no difference. So we see these two are equal, so that's good. All right, next problem. Consider a low system, blah, 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 right? So this is a free moment, so we can move this wherever we want and replace the system by equivalent force system and moment at origin. Oh, okay, so let's just do two things. Force and moment at origin O. Okay, so let's find, wait, how do we do this? I mean, the resultant force is just going to be this, right? Yeah, that's going to be the resultant force. It's going to be the sum of the forces, and there's only one force, so the resultant force at origin O is just going to be the sum of this, which is, we can write that out. Force resultant is going to be equal to force, which is 80, along the x-axis. So it's going to be cosine, because we want this value, which is adjacent to 60, so we want cosine 60i. In the j direction, looks like 120, so cosine 120 in the j direction. In the k direction, against the positive k, so we're going to have 45, so wait a second, plus cosine 45 in the k direction. That looks about right. So force resultant is going to be equal to 80 pounds times cosine 60 is 1/2 I. 120 is going to be negative 1/2 I, or 1/2 j, sorry. And this is going to be 45 square root of 2 over 2. Wait, no, what am I talking about? The x component is going to be 1 over square root of 2, yeah. Okay. So this is a resultant moment, resultant force at O, because that's the sum of the forces, which is only this one. The moment, we need to do the moment that this induced about point O plus this moment right here. So the resultant moment is going to be equal to the moment caused by F. Actually, let's write it out. So it's going to be the moment caused by F. Yeah, moment caused by F plus the moment, which is this right here, which is going to be equal to the moment that this induces about O is going to be a moment arm from O to A cross this, which is going to be equal to from ROA cross F plus the moment that we're given here. So let's find OA. So ROA is going to be equal to RA minus RO, which is going to be equal to A, which is in the x direction, what am I doing? In the x direction, it's -3. In the y direction, it's -4. In the z direction, it's 6. O is going to be 0, so that's it right there, I think. Hopefully I don't mess this up. That'd be kind of embarrassing. So okay, now we need the force, which we have right here, I think, right? Yes. Okay, so let's do our cross product. So let's do this part right here. So ROA cross F is going to be equal to IJK ROA, which is -3, -4, 6, and then this will be 1/2, -1/2, and then 1 over square root of 2, and we'll have our force, which is 80. Looks about right. This is going to be equal to, just do it out. I don't really feel like doing it. I'm just going to write down the answer. It's going to be 13.73 I plus 409.7 J plus 280 K. And this is in feet pounds, because feet and pounds, obviously. Now that we have this, we can add, so resultant moment is going to be equal to this, which we just found, so this entire thing, plus moment O, which is this. So let's write our moment O. Not moment O, what am I talking about? Just moment. The one that's given is going to be equal to 350. Okay, how do we do this? 350 times the direction, I guess. So the direction is going to be in the x direction. We need this component projected on the xy plane, which is this right here, and then we need to take the x component of that, which is this right here. So basically, what that means is we're going to do cosine 60 to find this component, and then do a cosine 70 to find this component here in the x direction. So cosine 60, that's going to give us a projection on the xy plane, which is this right here, and then times a sine 70. And this is going to be in the I direction. Also, also we need one in the y direction, which is going to be the opposite of that. So it's just going to be sine. Wait a minute. Did I just do sine? What am I doing? Okay, I meant sine. I meant cosine. Oops. This is cosine 70 I direction plus also cosine 60 times sine 70 times sine 70 in the j direction plus in the k direction, we're just going to have this right here, which is opposite to this. So we're going to use sine. So sine, I can't even read. What equals that? I think it's 60. So plus sine 60 in the k direction. Yeah, so you calculate this pretty easy, right? Distribute this out, blah, 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 right? Multiply this in, blah, blah, blah. And then you're going to end up with the moment is going to be equal to 59.85 in the I direction plus 164.4 in the j direction plus a 303.1 in the k direction. And this is in feet, pounds. And then now we can just do the moment induced by F. Let's call this moment induced by F. This is this. Plus the moment that's given is going to be equal to the moment resultant, which is going to be equal to. So basically, take this, and you would just add up the I components together, add up the J components together, and add up the K components together. Pretty simple, right? Add that up, and then you're going to get the resultant moment, which is going to be equal to 73.58 I plus 574.1 J plus 583.1, 583.1 K feet pounds. So now we have a resultant moment. Now what does it ask? And there's a train outside. Okay, great. So we did part A, resolve the force into, where you resolve the moment to components parallel and perpendicular to the resultant force. Okay, this is pretty easy. So basically what it wants us to do is we need the moment perpendicular and parallel to the force, right? How we do that is if we want something parallel, we'll just do the dot product. So let's see. So moment parallel is going to be equal to, we need the dot product, so we need the direction of F, which is going to be unit vector. So unit vector F dot mr, the moment resultant. That's going to give us a moment, but we want a vector, so we're going to do m parallel is going to be equal to F dot mr, because this is going to give us a scalar. We want a vector. We want the moment in that direction, so we just multiply by that. Okay, and let's see. And we also want a moment parallel. Perpendicular. So this is going to be equal to the moment minus moments parallel once we find that. And unit vector at F is going to be equal to these directions. So So 1/2 I minus 1/2 j plus 1 over square root of 2k. This is the direction cosines, basically, where it is. And then now that we have this, we can just do the unit vector at f, so the direction in f, dots with the moment resultant. And it'll just be this entire thing right here. This entire thing dot uf. So basically you would take this term multiplied by this term plus this term multiplied by this term, forgot the negative, and then add them. You know how to do a dot product. I'm not gonna do that. Everybody knows how to do that. So parallel is going to be equal to, just add them up, not that hard. It's going to be what? 81 I direction minus 81 J direction plus 114.6 in the K direction. Okay, good. Now that we have that, that's actually not right. Oops. This is actually a vector. When we do the dot product first, we're actually going to get not that. What we actually will get is once we do the dot product, we're going to get is going to be equal to 162.1 feet per pound. This is what we will get, actually. And then once we get this, we multiply this by the direction, we're going to end up with this. So basically, take this, take the moment resultant, which is this right here, multiply, or dot product it 2 times, basically. It's pretty simple. We're dot product it once and then multiply it. Now that we have this, we can do the moment perpendicular, which is going to be equal to the moment minus the moment parallel, which is going to be moment perpendicular is going to be equal to this moment right here minus this, which is going to be negative 7.42 I plus 655.1 J plus 468.5 in the K direction, and that's feet pounds. What else does it ask? Find blah 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 to make this into a wrench. Okie dokie. So now, this is probably the hardest question to ask on the test. But if you think about this, basically a wrench, we need this component right here. So, and it's on the XY coordinate plane. So somewhere around here, let's just say point's right here, right? This point is going to be X comma Y. And the vector from O to this is going to be equal to X I plus Y J. And we want this to be equal to, we want this crossed by the force resultant, and we want it to equal to the moment perpendicular. So what we will see is I can't write R, the moment from 0 to P, which is going to be RP, cross force resultant. This is going to be equal to the moment perpendicular. And RP is going to be equal to, we wrote that out earlier, and it's XI plus YJ cross FR is equal to moment perpendicular, which is going to be equal to IJK, and it's going to be X, Y, 0, which is this right here. FR, resultant force, remember we did that all the way up here, which is just this right here. So we're going to have 1/2, negative 1/2, and 1 over square root of 2 times 80. Yeah, just solve this. Pretty simple stuff. So this is going to be equal to negative 7.42 I plus 6.55 Wait, what am I doing? No. 655.1 J plus 468.5 in the K direction. This is feet, pounds. I don't want to keep writing that, but we have to write the units now, or else we're gonna get points taken off. There we go, blah blah blah, right? What else do we need? Find the position in the XY plane. Okay, so now that we have this we must set equal to moments perpendicular. Wait, this is the moment perpendicular. Oh, wait, oops, oops, oops. This right here is actually equal to, so basically if we do this out, it's going to be 1/2 in the I direction. And the I direction is going to be 1/2, 1 square root of 2 times y in the I direction minus 1 over square root of 2 in the j direction plus negative 1/2 x minus 1/2 y in the k direction. This is going to be equal to, what am I doing? This is equal to this right here. And just take a look at the y component, I mean the I components and the j components, I guess. So the I components and I components obviously have to be equal to each other if the moments are equal to each other, right? So we can just write 1 over square root of 2y is equal to this I component, which is going to be negative 7.42, and the j component, which is 1 over 2 square root of 2j, what am I doing? Whatever j is equal to this right here, 655.1. Wait a second, this is not right. Blah, 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 blah. Forgot x here. There we go. Solve for x and y, pretty easy. X is equal to negative 11.6. Why did I write it over here? Oops. Solve this for y. Y is equal to negative 0.131. X is equal to negative 11.6. So this is your answer basically, pretty easy. Put in coordinates, obviously. Negative 11.6 comma negative 0.131. If you want to check, take this answer and plug it in here, and that should equal to, in the k direction, but it's going to be equal to, so I'm not going to do it. So here, replace the blah blah blah. What is this called? Coplanar, whatever, I don't even care. It doesn't really matter. Just sum of the forces in the y, sum of the forces in the x, and then we can move it wherever we want. So we have to draw a free body diagram, else we're going to lose points, so let's draw that right now. This, right? And then we're going to have force down, force up, force this way, force this way. 675, 300, 450, 300. And what is this? 3, 4, 5, 3, 4. I feel like on a question like this, drawing a free body diagram does not really help that much, but we have to. So let's do some of the forces in the x direction first. This is going to be equal to these forces. We can neglect; they're not here. This one right here is going to be in the positive direction. I'll also draw this. If we don't draw this, we'll lose points too. So this point right here, and that's positive direction. This is going negative direction. So we have 675 times 3 over 5 in the positive direction minus, this is going in the negative direction, which is 300, 4 over 5. Some of the forces in the y direction is going to be equal to, this is going up, so 450. This is going down, so negative 300. This is going down. This is going up. Let's do the positive one, or I mean the negative one first. So minus 675, and it's going to be 4 over 5. This is going up, so it's going to be plus 300, 3 over 5. Solve this, solve that, blah, 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 right? We're going to get 165 in the I direction. This is going to be negative 210 in the J direction, right? So force resultant is going to be equal to 165I plus, minus 210J. Pretty simple stuff. Some of the forces in X, some of the forces in the Y. What else does it ask? Requiring as few forces and moments. Because this is all in the same plane, we can reduce it down to one. Moments, let's do the moment about A because I feel like it. So the moments about A, this vertical direction cancels. This vertical direction we don't need. So let's write that out. Some of the moments in A is going to be equal to, so these two are obviously going to cause a moment. Let's just do it simple. So let's go, it's going to be, what am I doing? Why did I write that? Okay, so this one right here is going to cause it in this way, which is positive. So it's going to be 300 times the moment arm, which is 1.5. 1.5 times 300. And this is 450. In the opposite direction, it's going to be negative. Negative 450 times moment arm, which is 0.5. 0.5. And then we'll have this in the x direction, which is going to be negative also. So minus 675 in the x direction, which is going to be 3/5. And this is in the going this way, which is in the positive direction, plus 300 in the x direction, which is going to be 4/5. Yeah, just put that in a calculator. It's not that hard. I'm not going to do it out. This is going to equal to negative 547.5. And this is going to be Newton meters in the k direction. So some of the moments, or just the moment result. I don't know why I wrote some. There we go. So we know that this is negative. So around A, if we have blah, 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 right? And we want specify where the line of action. Okay, so x equals 3y. So x equals 3y. Y is going to be equal to x over 3, which is 1/3 x. So the rise is 1 over the run, which is 3. So rise, let's call this 1 and 1, 2, 3, right? So it's going to look something like this. And we know that this is going to, so right now the resultant force is, so positive I, so somewhere maybe over here, and then negative, so it's going to be, the resultant force is going to look something like this. So this is the force resultant. And we know that the moment caused by this is going to be negative direction, which means here. It's like going this way. So we know that we need to move this up this. So it goes like this. So we have the force somewhere over here, which is going to cause a moment in the negative direction. Wait a minute, what am I talking about? Does that even make sense? Yeah, that makes sense. Okay, we're good. Because this is negative direction. Okay, so we need to know this so we need to know this x and this y coordinates. How can we do that? Actually, I have no idea. Loki forgot. I mean, we can just do like, wait, how do we do this? Let's call this point P, right? P is going to be a point which is going to be equal to x comma y. Y value is going to be x over 3. Let's call this xp, and this is going to be equal to xp. Wait, why did I write equals? So we need a coordinate, well, we need like a point. So p is going to be x, y, and y is equal to xp over 3. And, okay, so we have a point now. So if we do a vector, if we do a vector from O to P, which is OP, which is equal to RP, which is the same thing, right? If we do this cross the force, this force right here, so force resultant, this needs to be equal to the moment, which is this, which is equal to the moment R, like this, the resultant moment. That makes sense. Okay, so now that we do that, we need to add a new page so we have more room, blah, blah, blah. So what is RP? RP, we have this, that's RP. Cross FR, which we also have somewhere, which is this right here. So our resultant moment is going to be equal to IJK XP, and this would be XP over 3, 0, and then let's write this technically is equal to XP divided by 3. here, we have a vector now. So 165 and negative, okay, so 165 and negative 210, 0. Do the cross product, we're only going to get one in the k direction. And we're going to end up with something. And that something is going to be uh, 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 a bunch of random stuff. And then, wait, what am I doing? Oh, yeah. In the k direction. So we still need to do the k direction, which is going to be this times this minus this times this. Pretty simple stuff, right? So negative 210 xp time minus 165 xp divided by 3. That looks about right. Which is going to be equal to negative 547.5 pause. Which is going to be equal to, yeah. This is the moment MR. 7k Newton meters. And now we can just solve for xp. This is equal to this. Solve for xp. xp is going to be equal to 2.07 meters. Now that we have that, we know that y is equal to xp divided by 3, which is going to be equal to 0.689 meters. So our coordinate is going to be 2.07, 0.689 meters. So now we can just plot that. It's going to be somewhere over here. It doesn't really matter. That's our point along that line. Okay, now we want to, what are we doing here? Falling slab, blah, blah, blah. Okay, what should the magnitude of this and the magnitude of the resultant force are? Okay, so the magnitude of resultant force R is pretty simple. Fr, what am I doing? Fr, remember this is the sum of the forces. So we can see that sum of the forces is all pointing down, so we can just do Fb plus. Okay, they're all going to be negative, right? So we can just like write it all out and then put a negative sign on it. Or we can just write it out normally. Just write the negative sign. Okay, so negative Fb minus 60 minus 180 minus 40 minus Fa. And that's going to be negative 288 minus Fa minus Fb. So if we draw another system out, right? If this is, okay, that's a really bad drawing. Oops. Oh my gosh, that's even worse. Okay, there. X, Y, Z. Okay, so we'll just put this force, resultant force, force resultant in the center. And let's call this system 1. This is system 2. And we can also find the, what else were we trying to find? Fa and Fb. Okay, so we need 2 more equations to find that because we have 2 unknowns, so we need 2 equations or whatever. We can do we can do the moment about x and the moment about y of system 1. And that's going to be equal to the moment that Fr is going to cause about x and y at system 2. So 1.5 plus 6 is going to be 7.5, 7.5, and this is going to be 5 plus 1.5, which is 6.5. So if we do the moment, let's do the moment of system 2 because that's going to be easy. So the moment of around the x, this is system 2 is going to be equal to, in the x direction, so we're going to have the moment arm, which is 7.5. 7.5 7.5 times FR, and MR in the y direction is going to be 6.5, which is this right here. 6.5 times FR, and that's going to be both in the this way is negative. Okay, so this is going to be negative, this is going to be positive. So basically, that's what we need, and some of the moments about in the, okay, this is going to be kind of annoying to write, but the moment of x of system 1 is going to be equal to these two forces right here, so, and all of this is going to be in the clockwise direction, which is going to be negative. Yeah, okay, so negative 1.5 times FB plus 60, and then minus 180 times the moment arm, which is 1.5 plus 6, which is 7.5, and then both of these times the moment arm, which is what? 6 plus 6 is 12, so 13.5 minus 13.5 times FA plus 40. So that's going to be some of the moments around X. It's going to be a moment around X, which is going to be equal to, put that in your calculator, it's going to be 1320 plus 1.5 FA plus FB. Okay, now let's do the moment around Y, about I of system 1. This is going to be equal to, so we're going this way, so it's all going to be positive, which is nice. So 60 plus 40, which is 100, times the moment arm, which is 1.5. So 1.5 times 60 plus 40, which is 100, plus 180 times the moment arm, which is 6.5. 180 times 6.5 plus FB plus FA. FB plus FA, they're both multiplied by the same moment arm of 1.5 plus 10, so 11.5. Do that out, it's going to be, oh, wait a minute, what did I just do? Okay, this is not right. This is going here, actually. This is actually equal to negative 1980 minus 113.5 FA minus 1.5 FB. And basically we're saying that this and this needs to be equal to this and this, which is pretty simple. Okay. So some of the moment Rx about system 2 is going to be equal to, do this times that, and it's going to be negative 7.5 times 288 plus FB plus FA plus FB. Oops. I don't know why I wrote it like that. FA plus FB. Now that we have this, we can just solve. Pretty simple. Negative 2100 minus 7.5 FA minus 7.5 FB. So this is the X, this is X, this is Y. So moment about Y is of system 2 is going to be equal to negative 7. The moment arm is just 6.5 this time. 6.5, which we have 6.5 times FR, which is going to be 288 plus FA plus FB. This is going to be equal to 1820 plus 6.5 FA plus 6.5 FB. And this is going to be Y. So we can just set these two equations equal to system 1's equations. So basically set this one equal to this, set this one equal to that. and then just solve for FA and FB. System equations, not really that hard. If we do the first one, if we do this one equal to this one, what you end up with is FA minus FB equals 20. Set the second one equal to each other, we're going to have FA plus FB is equal to 100. And again, this is solved by setting x of system 1 equals to x of system 2. This is y system 1 equals to y system 2. The moment. Now that we have this is pretty simple. If we take this equation, add it up, we're going to get 2FA is equal to, this cancels, and that's going to be 120. So FA is equal to 60. Now that we have that, we can just plug into any of these equations. So 60 minus FB is equal to 20. So add this over, subtract the 20 over, FB is equal to 40. Okie dokie. Now, we can take this. Now that we have this, we can just plug into the reaction force. And so we have negative 1, so negative 288 minus 60 minus 40. And this is going to be 380, equal to negative 380. That's the force resultant. And let's read the question. What is the magnitude? So the magnitude is going to be equal to the absolute value of negative 380, which is going to be 380. And it's going to be kilonewtons, and that's our answer. Pretty simple, don't overcomplicate it. Okay, so this now. Circular door, weight of 55 pounds, so weight 55. Draw a free body diagram, circle. Okay, this is actually a pretty good question because we have a bunch of moments. All right, let's do this. Circular door. This is this is the z direction. This is the x direction. This is the y direction. If we take a look at this hinge, we notice that we can't have any moments going in the z direction. We can have moments about the x direction, but we can't have any moments going in the y direction. So we have moments here and here. Let's draw them all positive. So this one's here. Moment z. And wait, no, that's negative. Moments y. Okay, let's draw this a little bit prettier. There we go. And what other forces do we have? We have a force BC here. Let's just call this, yeah, so force BC. We have a weight going straight down. And weight is equal to, let's give us, yeah, so 55 pound. And looks like from here to here, this is 45. What other stuff do we have? We also have, this resists forces in the X, Y, and Z direction, this hinge, because this entire door can't move, obviously, anywhere. So we're going to have positive X, so hinge, let's call this AX. This is going to go this way, AY, and AZ, because it can't move in any of those directions. Okay, now that we have that, we can just sum the forces to X, sum the forces to Y, blah, 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 not that hard, right? So we don't know what this is. We need to know the direction, obviously. So let's do so we need to find the unit vector. So unit vector of BC. Let's go from CB, unit vector CB. So this, and we can cross it with whatever later. Unit vector CB, so RCB. So we need to find RCB is going to be equal to RB minus RC, which is going to be equal to, okay, so B, what do we have here? This point right here is, so B is equal to, in the x direction, we just have this, which is 3 sine 45. Yeah, because this is opposite to this, so 3 sine 45. 3, what am I doing? 3 sine 45, comma. In the y direction, we have this distance plus this distance. This distance right here is 3, plus this distance, which is 3. Okay, this is going to be long. We're going to have 3 plus this distance right here, which is going to be 3 cosine, which is adjacent. So 3 cosine 3. Just kidding. 3 cosine 45. In the z direction, we're going to have 0. C is going to be equal to, in the x direction, we're going to have 0. In the y direction, we're going to have 0. In the z direction, we're going to have negative 6 because the diameter is 6. Negative 6. Okay, now we can just 3 sine. Okay, we don't have to do that. That's going to take too long. Basically, it's going to be this minus this. So it's going to be a positive 6. Everything else is going to stay the same. So 3 sine 45, comma, 3 cosine 45 plus 3, comma, and then positive 6. Okie dokie, now that we have this, we can find the unit vector. So unit vector is just this divided by this squared, plus this squared, whatever, right? I'm not going to do that. You can do that yourself. CB is going to be equal to 0.26 in the I direction plus 0.627 in the J direction plus 0.734 in the K direction. Now that we have the unit vector, okay, now that we have the unit vector of CB, we can start doing some of the forces in the X and the forces in the Y. Okay, so some of the forces in the X direction is going to be equal to this component in the X direction, which is going to be equal to F, B, C in the X direction, which is this, times 0.26 plus AX. What else do we have in the X direction? Looks like nothing. So this is going to equal to 0. Some of the forces in the Y direction is going to be equal to so FBC in the Y direction is going to be this. So 0.627 plus AY. Anything else in the Y direction? No, that's all. Is equal to 0. Some of the forces in the Z direction is going to be equal to a negative weight, which is going to be negative 55. Yeah, negative 55. And then plus FBC times this Z component, which is going to be 0.734. And we have a Z also, which is in the positive direction. So plus A in the Z direction. This is going to be equal to 0. So we have our sum of forces. We also need to do some of the moments. Let's do some of the moments at. So if we have moments like this at one point, let's just do it the moment at that point because it's going to be really, really hard to do it. Actually, it's not going to be that hard, but let's just do the moments at A. So moments at A. Let's paste this over here so we can see it. So moments at A, we're going to have obviously this one, and it's going to be equal to mz in the K direction, in positive direction, plus my in the J direction. So all of these forces here, they don't do anything. So we have a force here which does something, which is going to be the weight times 3, I think. Yes, so we're going to have 3 plus 3, which is in the 3, which is from here to here, which is in the J direction. 3J cross weight, which is in the K direction. To cross 55K, it's going to be negative 55K. J cross K is going to be JK is going to be I. So we're going to have and it's going to be in the I direction. So 3 times 55 is going to be 3 times 55 in the I direction. It's going to be negative because of this negative. Plus this. So plus from here to here. So what point is that again? That's B. So RB. R from O to B cross FBC. And we need to find out where O to B is. So ROB is going to be equal to, okay, we need to find what point B is. Oh, we already did that. It's right up here. Okay. So it'll just be, let's just write it out. 3, what is it? 3 sine 45. Okay. 3 sine 45 in I direction. And in the I direction is positive, and the Y direction is also positive. Plus 3 cosine 45 plus 40 or plus 3. Remember, so the radius plus this distance right here, and the J direction, and then the K direction is 0. So it's just that, I think. Yep. And then we have the force BC. Do we have that actually? We do. We have the unit vector, so we can just multiply. So we know that the force BC is going to be equal to the force BC times the unit vector BC. Okay, now that we have that, let's just write out R from A to B, which is same thing as OB, which is right B, assuming that A is the origin, obviously. Cross FBC is going to be equal to, I have I, J, K. It's going to be a 3 over square root of 2. So this cross this. This is going to be 3 plus 3 over square root of 2. This is going to be 0. This is going to be, we can write F, B, C out here. And then we just write the unit vector BC in here. Unit vector is this right here, so we can just write that 0.26, 0.627, 0.734. Now just do some little bit of cross product here and there, you know, pretty easy stuff. You're going to end up with 3.76 F BCI minus 1.56 F of BC in the J direction plus 0 in the K direction. And this is equal to this part right here. And so what did we just find? We just found this moment here caused by this. If we collect every single term, like sum of the moments, so if we do sum of the moments in A in the x direction, this is equal to 0. So we can put all the moments in the x direction equal to this. So we have this in the x direction. Wait, no, what am I doing? In the I direction, we have 1. That's it. Is that even right? It doesn't even look right. Wait. Okay, yeah, so if this is equal to 0, then we can gather that 3.76 F BC is going to be equal to all the other I components, which is going to be just this right here. Just this. 3 times 55. And then blah, blah, blah in the Y, and then in the Z, right? Equal to 0, equal to 0. We're going to get the Y, which is this right here, negative 1.56 FBC is equal to M in the Y direction. That's the only y direction. Yep, that's right. Okay, so, and then we're gonna, in the z direction, we're just gonna have 0. So 0 is equal to what? The only one in the z direction is here, so mz is equal to 0, mz. And then if we solve, okay, so we have 1 here, and we also have we have this, and we have our equations here. So let's see if we can solve for everything. I think we can. So we have f BC is equal to 43.9 pounds. If we have that, we have this, we can solve for m in the y direction, which is going to be 68.5 feet-pounds. Now that we have these three, so BC, MY, and MC. BC we have, so we can solve for AX. This is good, which is going to be equal to negative 11.4 pounds. If we have, do we have AY? We don't. We have FBC, so we can solve for AY. So AY is going to be equal to negative 27.5 pounds. Okay, so AZ is equal to FBC. We have this, so we can solve for AZ, which is going to be equal to 22.8 pounds. What does it ask us to solve for? Is that all reaction forces at hinge as well as the forces along strip BC? Okay, so we have force BC and all the reaction forces 3 here, and then the force here, so this is going to be 4. Actually, no. What am I saying? There's going to be 3 force, 2 moments, and then another one. So it's going to be a total of 3 plus 2 moments plus 1. So it's going to be a total of 6. So 1, 2, 3, 4, 5, 6. Okay, that's good. So we solved for everything. This question I kind of like. So we want to know. Okay, so bearing blah blah blah. So let's draw a free body diagram first. So we have a force going down this way. Bearing B, it tells us, is a thrust bearing. That means it can't, it's going to resist load in the x direction. This is y. This is z. This is x. Okay, so we're gonna, this is b. This is c. Positive x, positive z, and positive y direction. C is only going to be positive this and this. It's not going to have a cx direction because it's not thrust bearing. Obviously, we have a force here. That looks like all there is. That's pretty simple, right? Okay, so let's do some of the forces in the x direction, which is pretty simple. Some of the forces in the x direction is going to be equal to 0, which is going to be equal to if this is b and this is c, so it's going to be bx. Therefore, we can conclude that bx is equal to 0. Let's do some of the forces in the y direction. Some of the forces in the y direction is going to be equal to 0, which is going to be equal to by plus cy, and then part of this force, which is, does it tell us the force is equal to? Wait, does it not tell us? What is the weight of the object and the reaction of the two bearings? Wait, how are we supposed to find this if it doesn't? Oh wait, this is, oh okay. This is the it's the magnitude and direction. Okay, so we're good, yeah. And we want this in the y direction, so it's going to be minus 45. Is that even right? That looks a little goofy to me. In the y direction. Oh, and we also have the weights in the y direction, which is down, so minus weight. Okay, so we have by plus cy is equal to 45 plus weight from some of the forces in the in the y direction. Some of the forces in the z direction is going to be, so some of the forces in the z direction is going to be equal to bz plus cz, and then the z component of this, which is negative 15. So we're going to get 15 is equal to bz plus cz. And let's do the moments x, the moments y, moments z. Because we can't really solve, like, can't solve for any of this right now. There's a lot of forces at B. Let's do some of the moments at B then. Actually, let me think. How do we want to approach this? What are we trying to find? Okay, so the goal of this is what is the weight of the object and the reaction of the two bearings. Okay, if we do some of the moments at B in the x direction. Okay, that's gonna work. If we just do some of the moments in the x direction, along this direction right here, we have this and this. Because this is known, we can find the weight. So let's do some of the moments in the x direction. This is gonna be equal to this distance right here, which is gonna be what? 100, 100, and this distance right here is just 200. And we know that they're going opposite to each other? I don't know. So around B, this is in the positive direction. So it's going to be the weight times 100. And then we'll have this other thing right here, which is going to be... So the only one that's going to cause... So the only one that's going to cause moment in the x direction. So the only one that's going to cause moment about this x-axis is going to be this y component, which is going to be negative 45. So it's going down 45, so it's going to be the positive direction. I mean the negative direction, so minus 45 times 200. And I mean, we have these terms, so we can solve for W, right? So W is going to be equal to 90 newtons. Pretty easy. Now that we have that, we did a sum of moments about the x-axis. What else can we solve for? Looking at B, if we do B, all these forces will cancel. If we do it along the Z direction, okay, if we do it along this direction right here, this is known, this is known. That means we can calculate C, CY. Okay, so let's do some of the moments at B, some of the moments B, I'm trying to think. There's a lot of options you can do this, I guess, but I'm just trying to think what would be the easiest. What if we do some of the moments in the Z direction? We're gonna have these two unknown, so we're gonna have equation. If we do some of the moments in the Y direction, we're gonna have these two and this. Okay, so basically if we do some of the moments in the Y direction, we're gonna have these two unknowns and this known, so we can have, so we're gonna have B, Z in terms of CZ, and we have this and this here, so we can solve for that. Yeah, you can just do some of the moments. Okay, yeah, let's do that. That makes sense. So if we do some of the moments, there's so many ways you can do this, bro. Some of the moments in the Y direction, this is gonna be equal to 0, and then we're going to have the Y direction, we're gonna have is equal to BZ, which is this right here, times the moment arm, which is this right here, and that is 50. and that's going in the negative direction. And minus c is going in the same direction, so cc times 150. And then we'll have this one right here in the z direction, so negative 15 plus, let's do minus 15 times the moment arm, which is going to be this entire distance, which is 200. And then what else do we have? What else do we have? I think that's all. Yes, we have BZ in terms of Z. So BZ in terms of CZ, we can solve for that here. And let me see if this is right. I think this is right. This looks right. Is there anything else that will cause moment around this? Wait. There is. A force in the x direction. Oh, yeah, that will work. So 15 in the x direction is going to cause moments. What is this? Let me think. Negative. So negative. So we have a positive x, so it's going to cause negative. And then in the y direction, and the z direction. So z direction is this way, negative 15. So negative 15. Wait, this is actually in the positive direction. This is a z direction because it's going counterclockwise. And the x component, which is 15, is going to be going this way, which is going to be in the clockwise, which is negative. So minus the x component, which is this way, times the momentum, which is 200. So 15 times 200. Okay, so we can see this actually cancels, so we just did all that work for nothing. So we can have this, which is pretty simple, add it over. So BZ is going to be equal to negative 3 CZ. So we have this other relationship that we gathered, and then from one of these equations, BZ, CZ, from this equation right here, a little bit of systems of equations, not that hard. We gather CZ is equal to 15 over negative 2, which is going to be equal to negative 7.5 newtons. And plugging this in here, we can find that BZ is going to be equal to 22.5 newtons. So take this, plug it in there. And that's all we can solve for now. Let's do some of the moments in the z direction then. So some of the moments in the z direction is going to be equal to so it's going to be this. They're both going in the positive direction, so BZ or BY, CY. Okay, so BY, that's going to be times 50. BY times 50 plus CY times, what was it over here, 150? Okay, what else? Looks like this is going to cause a moment about the negative direction, which is going to be going down, which is going to be clockwise, which is going to be negative. So negative 45. So this is going to be negative 45 times the moment arm from here to here, which is 200. Which is all going to be equal to 0. So from this relationship, we have a BY and a CY. So take this, plug it in for this, solve for one of them, and you'll end up getting, if we just simplify this a little bit, we're going to get BY is equal to 135 minus CY. And then from this relationship, in this relationship here, you can easily solve for stuff. And then once you solve, you're going to get Cy is equal to 22.5 newtons, and By is equal to 112.5 newtons. I'm not going to solve these because that's not what this is about. If you can't do math, then you shouldn't be even looking at this. I'm going to say that, and then this is like some of these relationships are probably wrong, but you get the general idea. It's okay if it's wrong sometimes, it doesn't really matter. It's just as long as you get the general idea. Okay, next one. Determine direction of A and B. Okay, so we can see that A is a thrust bearing, so we're going to have force this way, and then force in the positive x direction, and then also force in the y direction. B is just going to be x direction and y direction. Okay. A 115 Newton meter, okay, cable C and D prevents the plate and shaft from turning about AB. And we have a force going this way. Okay. You know, I'm not going to draw my free body diagram because this is not a test and you can literally see it right here anyway, so cable FC, let's call this tension. Why is that so long? Tension. There we go. Okay, so how do we go about this? A has a lot of moments, I mean forces, so if we do some of the moments at A, if we do some of the moments at A, we want to think, wait, this is also a force going down this way. 25, so it's going to be 25 times 9.8, 1. So weight is equal to 28. Is that 28? It's 25. 25 times 9.81, which is going to be equal to 245.25 newtons. Okay. How do we go about this? Okay, if we look at A, and then we go in the... If we do a moment about the z-axis at A, we're going to have this, which is known. None of these will come into any effect. This is not known. Okay, so yeah, then we can just find... Then we can find the tension, which is... Let's call this force. Is that right? I think that's right. Yeah, let's call this tension. Yeah, because the only one that's not known is this. And that's the only thing other than this that's going to cause moments about the z-axis. So let's do moment. We can just do moment z-axis. It's going to be equal to E0. Some of the moments is going to be equal to 0. And we're going to have... Oh, shoot. Okay, this is in millimeters. This is in Newton meters. Okay, so 150 Newton meters times... we need meters on the bottom. So 1 meter is equal to 1,000 millimeters. So it's going to be 150 times 1,000, which is going to be 1.5 times 10 to the 5th power. And that's going to be Newton millimeters. Now our units match up. We can do equals 1.5 times 10 to the 5th power Newton millimeters. We'll have this moment, which is in the positive direction, times, not times, what am I doing? Minus, this is causing moment in the negative direction. And we will need the this value right here, which is going to be perpendicular to the y-axis, which is, yeah. So we have a triangle. If we divide this by 2, no, if we divide this by 250, we get 750 divided by 250, which is 3. This is going to be 1. That means this is going to be the square root of 9 plus 1, which is going to be 10. We want the direction this way, which is going to be 1 over square root of 10 minus 1 over square root of 10 times the force, which is T, times the moment arm, which is this distance right here, 750. Okay, now that we have this, we can, we have everything, so we can just solve for T. So T is going to be equal to 632.46 newtons. Okay, now that we have this, let's do, what else do we need to solve for? So we have T, we want reactions at A and B. That's our main goal. Okay, so I'm trying to take a look at this and see what we can do to find what we're looking for. Okay, if we do, moment around this, we're gonna have this one and this one. So we can find A Z by doing a moment about B in the y direction. So by moments of by is going to be equal to 0. I think that would work in the y direction. Oh my goodness. Okay. There's just so many ways to do this. I'm trying to think of the easiest way possible to like solve this. If we have this, we'll have the only thing that's causing moment is this one, and this one. Okay, yeah, that would work too. If we do AX this is going to be equal to 0, right? So we're going to have by times 250, and that's going to be in the positive direction, so it's going to be by times 250, which is, do I have by? I don't, wait. By times 250. That's in the positive direction, minus, we're going to have the weight divided by, times this divided by 2, so 750 divided by 2, I don't even know what that is, like 375, minus the weight times 275. Sorry. Minus, and we'll have this right here, which is going, we'll need this component right here, which is going in the negative direction, which is going to be 3 over square root of 10. So 3 over square root of 10 times tension. And that's going to be times the moment arm, which is going to be from here up to A, which is going to be this plus this plus this. So 100 plus 500 is going to be, so it's 850. We'll have this, and this will be equal to 0. Solve for by. Weight is given this. So by is now equal to 2407.9 newtons. There's just so many ways you can do this. This is a pretty easy problem. Let's do, if we do a moment at A in the y direction. Yeah, now let's do a moment at A at the y direction. So we're just gonna have this and this one right here, I think. I think I said I wanted to do this earlier, so this is going to be equal to, so this is going to, so the bx, wait, is that bx? That's by. We're going to have this, which is the bx, so that's going to be in negative direction, so negative bx times, the moment which is 250. And then we have tension, and that's going to be this way, which is also in the negative direction. And that is going to be 1 over square root of 10. So minus 1 over square root of 10 times the moment arm, which is this entire distance, which we did earlier, which is 850, times t. Okay, so everything is given except for bx. So we can just solve for bx. So bx is equal to negative 680 newtons. Okay, now what shall we do? If we did some of the forces in the x direction, some of the forces, this is known. Bx is known, so we can solve for ax if we do some of the forces in the x direction. So some of the forces in the x direction will be equal to ax plus bx. Both of these added together plus this guy, which is going to be in the x direction is going to be 1 over square root of 10 plus 1 over square root of 10 times tension. So this is known. This is known. So we can just have ax is equal to 480 once you plug it all in and solve. Okay, some of the forces in the y direction, we have a by. We have this. This is known, so we can solve for ay now. So some of the forces in the y direction is going to be equal to ay plus by plus, okay, this is going to be minus because this is going this way, and it's going to be 3 over square root of 10. 3 over square root of 10t. This is known, we can solve for ay. Ay is equal to negative 1810 newtons. Ay plus b, yep, that's right. And then some of the forces in the z direction, what do we have? Do we have some of the forces in the z direction? It's going to be just this and this. So some of the forces in the z direction is equal to 0. And we're going to have the weight is going to be equal to a in the z direction. So the weight is 245.25 newtons, which is equal to 8 in the x direction. Sorry, in the z direction. The weight is known because we calculate that over here. Okay, next problem. Wait, are we done? Determine the reactions at A and B. Okay, so we're gonna have 3 here and 2 here, so it's gonna be 5 total. AY 1, 2, 3, 4, 5. Okay, yep, that's good. Okay. Free body diagram, I'm not gonna draw it because I don't feel like it. This direction, this direction, this direction. Obviously, we're gonna have a moment about this direction, the positive direction. We're not gonna have a moment in the y direction. We're gonna have a moment in the x direction. This will be moment z, moment x, and then ay, ax, az, obviously. It's pretty simple. We have a force this way, force down this way. That's all there is. Not that hard. We can do the moments. Yeah, let's do the sum of the moments. Okay, this is gonna be actually quite long. I'm not gonna lie. Okay. So some of the moments at A is going to be equal to mx in the I direction plus mz in the k direction. And pretend there's an A here. I just don't feel like writing it. And what else are we going to have? We're going to have this moment, which is going to be AC cross CB. So we're going to have a moment we're going to have a vector like from here to here cross this force. Okay, so plus the moment caused by the force BC at point A, which is going to be a vector R from A to C, cross the force CB, so tension CB basically. Let's call it force CB, it doesn't really matter. This is CB plus, we are going to have another vector here to here cross, so AD, so vector AD cross the weight has mass of 80, so weight is equal to 80 times 9.81. I wish you could use this 10. That'd be so much easier. Just be 800. Like, I don't know why we're not allowed to use that. Oh well. AD cross 80 times 9.81 in the negative k direction. Okay, so that's the moment at point A, I think. Let me check. Yeah, that looks about right. Okay, let's just sum of the forces x, sum of the forces y, blah blah blah, right? Do we even need to do that? We should probably find AD, AC, CB. We don't know what CB is. We definitely need the unit vector of CB. Okay, so basically the force, the force vector of CB is going to be equal to CB times the unit vector of CB. Let's find, okay, so B is going to be equal to, in the x direction 0, in the y direction we're going -1, in the z direction we're going 2, C is equal to, in the x direction we're going 6, in the y direction we're going 2, in the z direction we're going 0, D is equal to x direction 6, -2, 0. Okay. So AC, we need to find AC and AD. AC is going to be equal to C minus A. Wait, C minus A is 0, so it's just going to be, it's literally just going to be C then. Yeah, so it's going to be 6I plus 2J. AD is going to be equal to just D basically, so it's going to be 6I minus 2J. Let's call this M1, M2. M2 is going to be equal to 6I minus 2J cross 80 times 9.81 in the negative k direction. Negative k direction. So I cross k, I, j, k. I cross k is going to be negative j. So it's going to be 80 times 9.81 times 6 in the negative j direction. And then we're going to have -2. So j cross k, I, k is negative j. Jk is going to be I. And it's positive I, so we're going to have negative times negative, which is going to be positive. So we're just going to have plus 160, 2 times 80 times 9.81 in the I direction. That's going to be M2. Hopefully I didn't do this wrong, because that'll be quite annoying if this is wrong. It's probably not wrong, hopefully. Yeah, it looks about right. So M, we can calculate this out to be 1569.6i plus 4708.8j Newton meters, and let's write this here, and then M1 is going to be, we're gonna have to do a cross product here. I, J, K, RAC, which is over here, so 620, and FCB is going to be UCB. Okay, we don't have that yet. We need the unit vector. So CB, so RCB is going to be equal to RC, or RB minus RC, which is going to be equal to B, which is going to be 0, -1, 2, minus C, which is going to be 620, which is going to be equal to -6. 1 minus 2 is going to be -3. 2 minus 0 is going to be 2. 6, 3, 2. So we can divide that by 2 too. That's all going to be divided by the unit vector. Okay, that's going to be sorry, I was just talking to myself. This is going to be equal to -6, -3, 2, 636 plus 9 plus 4. This is equal to 7. Okay, we can bring the 7 out front. So -6, -3, 2. We can bring the 1/7 out front. We can actually pause. We can divide this by 2, so we can have 320, and we can have this 2 out in front too, so we don't have to do that much math. 2/7. This will simplify it down a lot, and then so moment 1 is going to be equal to, if you do this out, it's going to be 2/7, and this is moment 1 is times this CB, FCB, and remember FCB is going to be equal to FCB times unit vector in the CB direction. So we're going to have FCB out here too. So it's going to be 7/2 FCB. And then we're going to have 2 in the I direction, minus 6 in the J direction, minus 3 in the K direction. This is going to be meters. Sorry, I meant Newton meters. Yeah, this is it. Now we can take both of these, add it together, and then add this right here onto it. Basically, we have this, so add them together. We have this, add them together, right? So we can get some of the moments at A is going to be equal to, this is going to be quite annoying. We add them all up, basically, which is going to be very annoying, I'm not going to lie. Okay. So if we just look, we're going to have the I components plus I components, which is going to be 1569.6 plus 2/7 FCB times 2, which is making this 4. Do we have I components? We do, so plus mx and I direction. So from this, and then obviously add up the J, add up the K components, or whatever. This is all going to be equal to 0 eventually, so dot 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 is equal to 0, so we can just solve. So we just conclude that mx is equal to negative mx. So let's subtract this over to the other side. We're going to get 1569.6 plus 4/7 FCB. Let's see here. Yeah, and then you can just, from here, you can solve. You can get a ratio, right? You can get 6/7 FCB is equal to negative. What am I doing? you have this here, and then you have to solve a bunch of system equations, which I really, really do not feel like doing. Okay, what does it ask for us to do? Moments reactions at A. I mean, this is, you're basically done, and then set the, okay, set the J component. So, okay, let's do that too. 4708.8 J component. Here, J component, we're going to have minus 6 times 2, which is going to be 12 over 7 FCB. Is there any J components up here? There's not. So this is equal to 0. So we're going to have 12 over 7 FCB is equal to 4708.8. We have this. And then we set the Z components equal to each other. We have all these equations. Dude, wouldn't it be nice if we could just plug this in our calculator, right? System equation solve, but it says we need to solve manually, so oh well. In the Z direction, blah blah blah. Z direction here. So we have negative 3 times. So negative 6 over 7 F CB. And there's a Z direction up here. MZ plus MZ is equal to 0. So we're going to get 6 over 7 FCB is equal to M in the Z direction. Okay, yeah, that's pretty good. And we have our, so basically we have CB, CB, CB. Okay, basically now we have all the equations we need to solve for everything. And how would we go about solving this? Let's take a look. FCB, MC, 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 blah, 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 blah. Wait a second. From this, we can solve for FCB. So basically 7 over 12 times 4708.8 is going to be equal to FCB. And we can conclude that FCB is going to be equal to 2746.8 newtons. Now that we have this, where can we go from here? CB, CB. Okay, so we have this. We can plug this in. We can solve for mx. So mx is going to be equal to, take this, plug it in here. Mx is going to be equal to negative 3139.2 Newton meters. Now that we have this, we can, okay, we have CB, so we can plug this in here to find MZ too. So MZ is going to be equal to 2746.8 divided by 7 times 6, which is going to be equal to 2354.4 Newton meters. And that's it. GG's. Pretty easy, pretty chill. Okay, that's all.